Good, so I'll start. So what we were discussing yesterday was still in the context of calculating the entropy of the region A, which we took to be an interval in a two-dimensional CFT. We had on the board these pictures of the state prepared in three different coordinates. So three different geometries that are conformally related. Okay, so we ended with drawing the reduced density matrix rho sub A. And so let me remind you of that figure in the three different geometries. Sorry. Okay. So we had this one, which was the regular one. Then the one where the interval is mapped to the infinite half line. So if this was in zeta coordinates, this was in W coordinates. And then the important one for a connection to thermal entropy, which we'll discuss today, is the third one in terms of Z coordinates. Okay. So let me again color the A region in red in all of these pictures. So here, 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 and here. So this is an OR. So we can either write or draw this picture as the strip or as the cylinder. Okay, and then yesterday also what I added was the cylinder time. So the Euclidean cylinder time tau. I added it in each picture so you can track where it's going. Also in the previous geometries, okay? So this is always the direction of tau in green. So all of these are path integrals, but okay, so you can draw the path integration like this. Okay, so everyone happy with these reduced density matrices? Good. So if you would trace them also over A, then you would get the plane, the annulus, and the cylinder. So I'm going to refer to these coordinates sometimes as zeta for the plane, W for the annulus, and Z for the cylinder, okay? Let me not write the fully traced ones. It's clear that where they will close up, right? They close up at the red lines, you get the plane, the annulus where this is now closed, or the closed cylinder, okay? Just a cylinder. Good, but going back to the reduced density matrix, this is a matrix. It still has two slots where you can enter a boundary condition field configuration, okay, which is exactly where the red region is. So let's do that. So let's consider matrix elements of that reduced density matrix. So we had two notations for that. It's taking the phi primed element of this matrix, if you want, is contracting the reduced density matrix with these field configurations. Phi prime will go here, phi here, phi prime here, phi here, phi prime here, phi here, okay? So technically, I would have to change my dashed lines into full lines when I write these boundary conditions, okay? But sometimes, so also in the notes, I have this notation then that I put these in brackets, meaning if you want to add them, this is where you add them, okay? So if you add them, you get the matrix elements. But now there's a nice interpretation that you see appear in the second and in the third picture. Let's start with the third picture. What we actually see now is that rho A gives us the evolution from the state phi prime in the tau direction to the state phi. Okay, so this is what you can now read off from this path integral picture. So this is equal to the evolution from the state phi prime to the state phi, evolving in the tau direction. And you evolve in the tau direction over a distance 2 pi over kappa. So if you remember, when we drew the state in this third picture, we found that, like this. We found that A was on one side of a strip and A bar was on the other side of a strip, with the strip having a length pi over kappa, if you remember. So we had to double this to get to the reduced density density matrix. So this here is a strip of 2 pi over kappa, or if I write it as a cylinder, the periodicity here is 2 pi over kappa. Okay. So let me add that here. So we're doing evolution from the state phi prime to phi in the tau direction over a distance 2 pi over kappa. Okay, and I told you that kappa, it entered through the conformal map from this picture to this picture. And this kappa was an arbitrary real number that should not affect physics. So I can choose this kappa, I can choose it to be 1, which is a natural choice, or I can choose it to be 2 pi over some other random number, beta, so that the whole thing is a real number, beta. Okay? What I find then is that my rho A in this last picture is equal to the evolution operator for evolution in the tau direction over a distance beta. So it's this operator, e to the minus beta h tau. And the point is that what we saw in the past lecture is that this is a thermal density matrix, of course. So we found that by doing a smart conformal map from our interval to the half line and then, importantly, to the cylinder, that we've been able to interpret our reduced density matrix as a thermal density matrix, okay? So this works in the last picture, this interpretation that you're evolving your state phi prime to phi. It also works in this second picture, in this second picture here, where you evolve phi prime to phi in the direction of tau. So this works both, I call these pictures A, B, and C. So this interpretation here, it works in B and in C. So in the geometry, which we call dW, dW bar, and in the cylinder geometry, dZ, dZ bar. Okay, so let me write very explicitly what this h tau is in these two different pictures, okay? So, well, also here, of course, this is for B and C. So, like I said, this h tau is the notation for the Hamiltonian in cylinder Euclidean time tau. So in the geometry dz bar, which we have also written as d tau squared plus d r squared over r squared. Okay. Meaning it's the generator of translations in that direction tau. So that's for picture number C. And for the middle picture, you remember that tau is your polar angle of the disk. It's also in the picture, okay? So it's the same Hamiltonian is also the generator of rotation in the angular direction tau in the disk geometry or annulus geometry. Where tau is your polar angle, okay? So if it's the generator of rotation in this Euclidean coordinate tau, then it means it's a generator of the boost in the Lorentzian signature plane. So if you analytically continue tau back to Lorentzian time, then in that well, let me not say it like this, but in Lorentzian signature, by which I mean this geometry, this metric, it's a generator of boosts, okay? Okay. Then I mentioned this already, but let me say it explicitly again. This kappa we introduced as an arbitrary real number that the physics should not depend on. And so this choice of periodicity beta is also, in that sense, random. So by choosing kappa to be 2 pi over beta. Yeah. Okay, and this is because this thermal interpretation is in terms of a temperature beta, inverse temperature beta, that is fictitious, okay? We're still talking about a 2D CFT in a vacuum state and looking at a particular region of that A. But by doing these conformal maps, we've mapped our reduced density matrix to a thermal density matrix. And that temperature is a fictitious temperature that is measured by an observer that only has access to that region A, okay? Specifically to that region A in the second and the third picture, meaning has access to either half of the W plane or one side of the Z strip, okay? Okay, so this result that your reduced density matrix takes the form of a thermal density matrix, it's important enough that it has a name. So this is called the Bezold-Nano Wigman theorem. After the people that derived this using algebraic QFT. So what we have seen now is a path integral derivation of this statement in which you can actually pictorially understand why this is true. Okay. So one thing to add here is that maybe on this board, one thing to add here is that we were in the vacuum state in this picture. And so I mentioned that really, if you tell me you're in a vacuum state, you should tell me with respect to which time, so with respect to which coordinates. So in zeta coordinates, the state is the vacuum. In W coordinates, the state is still the vacuum. And I commented on this yesterday that this will be the case when your Schwarzschild contribution to the stress tensor transformation law is vanishing. Okay. And you can check that is the case for the type of conformal map that we did from here to here. But then going from here to here, you do have contribution which is responsible for this observer having access to the red region, measuring a thermal state in z coordinates. Okay. Questions? Yes?
Is there any insight why this conformal mapping from the middle to the right is somehow more special than from the left to the middle? Because now I pick up this thermal contribution.
Well, no, because also here I have a thermal interpretation. Just that here my periodicity of tau is 2 pi because I didn't introduce a kappa yet. And in the next step, I'm a bit more free to choose this kappa. But yeah, I see why you're asking this, because here now I said that this is the vacuum state. The reason you can read off the thermal interpretation here is because you're reading it off in terms of something that is not the actual W time. You're reading it off in terms of what is the polar angle, which will become a time here. It's just that this rotation you can already see in this middle picture. Okay, but really it's indeed the right picture to have in mind for the thermal interpretation, yeah.
I guess that the thermal state is not really a pure state, right?
No, it's like, yeah, it's, yeah. It's not.
I asked because you wrote a cat thermal, so
Ah, okay, yeah. Yeah, yeah, okay, so this is a loose notation then. The point is indeed this, so because I didn't mention this, I think. I mentioned in the beginning when we introduced the reduced density matrix that this will be a mixed state. If you trace out the degrees of freedom in a bar out of your pure density matrix, you will end up in general with a mixed density matrix. And here in this particular description, you end up with a very particular mixed state, namely the thermal mixed state, which is useful because the thermal mixed state we know how to work with. Yeah. Good. So. Okay, so let's go back to the entanglement entropy. So the entanglement entropy that we were interested in was the entanglement entropy in the z-plane for an interval A. The statement is that this is equal to the entanglement SA in the W annulus and equal to the entanglement entropy in the Z cylinder. Because we know we can derive this entanglement entropy from the correlator of the twist fields. Correlator of the twist fields is conformal invariant, so we're allowed to do these conformal mappings to derive our entanglement entropy. So this explains why that is true, and then we've now reinterpreted our path integral picture for the reduced density matrix in the cylinder as a thermal density matrix. Therefore, the associated von Neumann entropy is a thermal entropy now. Okay. So the thermal entropy, we wrote down all the way in the beginning when we discussed von Neumann entropies. And it's equal to 1 minus beta d beta, the log of the partition function of your thermal system. So this is the same as saying that your entropy in a thermal system is beta times the energy minus beta times the free energy. Okay? So this is just a standard statistical physics formula. And so here, z of beta is, like I said, the partition function of your thermal system. And we wrote it down for a general thermal system, a TVN system, last lecture. And in particular, we also wrote it down for a thermal QFT. And we worked out that that partition function for a thermal QFT can be interpreted as the Euclidean path integral over a closed path in Euclidean time with a periodicity beta. Okay, so you can write your partition function either as that Euclidean path integral over a compactified Euclidean time, or you can write it as the trace of the thermal density matrix, okay? Okay. So for us, this partition function is a partition function of a CFT on a strip of width beta and length LZ. So to distinguish it from the length measured originally in the zeta plane of the interval, so the length L of the interval in the zeta plane. So LZ refers to length in the XZ direction, which in this picture is this direction, okay. This is XZ. These were just the different coordinates that I introduced last time. So to distinguish it from X and TE here. Okay, and so this this partition function of such a CFT, it was determined by Cardy and Affleck in separate papers, I think. So the references are in my notes. And what they found was that that partition function is equal to some non-universal constant times beta times the length of the strip. So a non-universal meaning that this is CFT dependent. So depending on which particular theory you're looking at, and then there's a term pi c over 6 beta LZ. Okay, so to determine this, they also had to make use again of the Weil anomaly. So every time there's a C appearing in a 2D CFT result, your Weil anomaly is behind the physics of it. But didn't have time to discuss the Weil anomalies, but it's just a comment. Okay. So if you plug that result into the thermal entropy formula, you get this expression. So the CFT-dependent constant doesn't contribute because it's a term linear in beta, and that drops out of this this operation here. And so now all you have to do is write your length of the cylinder, again in terms of the original length of the interval, which is what you were interested in. And so to do that, you have to remember in this picture, from the actual conformal maps which we worked out last time, that here, so this might become a bit messy, but okay. So here the begin point was at epsilon, the end point was at L minus epsilon. And so because the map from the plane to the cylinder is the exponential map, or from here to here it's the log, we had here in this picture that this was the log of epsilon over L, 1 over kappa, and this was 1 over kappa log of L over epsilon. Good, so the whole LZ was 2 over kappa log L over epsilon. So if you plug that in here, you find indeed that the thermal entropy of that cylinder is equal to C over 3 log L over epsilon. These are now measured in zeta coordinates. So these are, this is again the result for your entanglement entropy that you were looking for, okay? Okay, so this Z of beta, the partition function is just the partition function for the system as it is. We haven't said anything about replicas at this point. We've managed to escape the replica method by mapping it to a thermal problem and then just having to use the thermal entropy rule for evaluating that. But we had to use, okay, this outside result from Cardy. But this is just to say that Z of beta is what before I've called Z1, okay? So it's the trace of one reduced density matrix. So these are the same. So let's try to understand why this gives us the same result as the replica trick. So now we go back to the replica manifold, but we'll write it for each of these conformally related descriptions, okay? So in zeta we had this picture, okay, you remember? So each of these copies is a reduced density matrix that's glued to the next copy, right? So this is our replica manifold that had conical singularities at the boundaries of the regions A, okay. Then in the W coordinate, our reduced density matrix, one copy of it is this. So you would have to make a bunch of copies of this and then attach. That would be the replica manifold. This would still have a conical singularity at the origin. Now let's do the same for the cylinder, or for the strip. If you take n copies of this, and you glue one to the next, to the next, to the next, you just make a very big cylinder, okay? So the replica manifold for rho A being the strip of length beta, or this open cylinder of circumference beta, we have that the replica manifold is just a large cylinder with, by large I mean circumference n times beta. Okay, so if that one upstairs, Z of 1 is just the cylinder with circumference beta, then Z of n I can write as Z of n beta also, okay? It's just the same notation as writing Z of beta as Z1 or Z of n beta as Zn, okay? Here I explicitly write the periodicity, okay? Like there. But the important point is now that the conical singularities have disappeared. Okay, we've pushed them to infinity by the conformal map. So this cylinder no longer has conical singularities. And this means that analytic continuation and the replica trick in this description is very straightforward. Namely, so the replica trick way of calculating as A is taking 1 minus n dn of log Zn and then n to 1. Okay, so if we do that in the cylinder picture, then Zn is just equal to Z of n beta. And then we use Cardy's result there. So this is equal to constant times n times beta Lz plus pi c over 6 n beta Lz. Okay. So this gives us a trivial n dependence that if you plug it in here, you will find just the same result as having used the actual thermal formula. Okay? Because your n just multiplies beta. So the point here is that we can make a replica manifold of any n times beta, also for n that are not positive integers. The restriction for n to be positive integers came from this interpretation in terms of n copies, okay? This is also how we constructed this z of n here, n copies of the cylinder. But now that we have this z of n, like this, we can just change the periodicity continuously. And so the analytic continuation, the reason that this is just equal to the thermal entropy simply is because the analytic continuation in this case is basically trivial. Okay. So what we've achieved is that by using the conformal invariance of the entanglement entropy for the first 3 steps up there, that allowed us to use different conformal maps. So the conformal invariance plus this trivial replica trick on the thermal cylinder gives us a well-defined analytic continuation in N. And this is partly why I didn't spend too much time on the previous mathematical explanation of the analytic continuation in this picture. So I gave you a reference, but if you map it to the thermal picture, then it's clear why it has to work. Okay. Yeah.
So can you see somewhere, like, if you just look at the entropy, and as you just said, you basically perform an analytic continuation through this change of geometries. Where exactly would be the step where we would have done it, like in terms of coordinate changes? You understand what I mean?
No, sorry. Can you try again?
I guess it's probably the last step, right? Like, if you just look at the change in the entropy in the entropies, then at some point this dependence on n vanishes, or just goes to 0 and infinity, or minus infinity. So this is, I guess, where you actually do, like, if you want to talk like this, like an analytic continuation in terms of this coordinate change. So the coordinate change does your analytic continuation in that step, right?
Well, I'm not quite sure I understand it completely, but the n dependence is still there in the step, in that n is here and here, but you've moved your conical singularities by the conformal. So there's no n dependence in the conformal map.
Right. Okay.
The conformal map was just taking zeta to L over zeta minus L, and things like that. There's only kappa dependence, which is like a fictitious temperature that arises.
Well, I think.
Yeah. Okay. So this encounter of an entanglement entropy being a thermal entropy, or a reduced density matrix being a thermal density matrix, that fits in a more general discussion, namely that of the thermal field double. And so that's what I want to discuss now. So it will feel very familiar because this is exactly an example of it, okay? So when do we have a break? 1:20, 2:20. Yeah. Okay, very good. So if I didn't forget to number my previous sections, and this is section 6. The thermal field double, okay. So let's do the opposite thing and start with the thermal system. So on the previous board, we started from the vacuum state, CFT, and then mapped half of it to a thermal system. Here we'll basically do the other direction, start from a thermal system and map it to the double, which is called the thermal field double, which will be in a pure state. Okay, but we start from a 1 + 1 dimensional CFT, which is living, or with states living in a Hilbert space, curly H, and I'll label that by R. It will be clear why, but this is the Hilbert space of the CFT, and the Hamiltonian of the CFT I'll label also by R. So this is the CFT with some temperature beta. So it has some thermal partition function. Which is a Euclidean path integral over a compactified Euclidean time tau. So I'm using here the same notation as we did for our cylinder. So, meaning my space-like dimension of the CFT is the xz dimension, and the time-like direction in Euclidean signature is tau. Okay. With a circumference beta. Okay, so this is the trace of the thermal density matrix. So the thermal density matrix itself, I can write as the partition function before we completely closed it, so like this. Okay. Okay, and now the general statement is that you can do some procedure called purification. And that tells you that the thermal physics can be described by a pure state, which is called the thermal field double state. So the thermal physics can be described by a pure state called the thermal field double state. The thermal field double state, I'll just write as psi like this. I'll give you a mathematical version, but it's defined pictorially as this state. So the one that you prepare by path integration over half the cylinder, okay? Half the cylinder, meaning that you evolve in tau for a period beta over 2 only. Not beta, but beta over 2. So the thermal state had this open region here over the full length of the coordinate xz. So in the original CFT, a state would live from xz is -infinity to infinity, which means it would live here along this line in this Hilbert space that I called the right Hilbert space, because now we've constructed a state that has that is living on two separate regions of x, z going from minus infinity to infinity. One is where the original right Hilbert space was, and here is where there's now a new copy called the left Hilbert space. So this state lives in an extended or doubled Hilbert space, which we now call the right times the left Hilbert space. Okay. I'll make that more clear now. Okay. So this state has is prepared on these lives on these open dashed lines. Okay, this is always where the state lives, and it can take on a field configuration living at the dashed lines, like always, to make a wave function, okay, wave functional. It's just so that in this case, the field configurations that you have to feed this thing consists of two sets of field configurations, which we can call a right copy and a left copy, okay? And if you feed it those boundary field configurations, then you can write down the wave functional, which is then the partition function with those boundary conditions, okay? So where the field at this value of tau, let's call it tau 0, for the whole length of the spatial coordinate should be equal to phi left, and then phi at tau 0 plus beta over 2 here over the full range of the spatial direction should be phi right. And so since this is now a wave functional dependent on two sets of field configurations, this is why it lives in the corresponding state lives in a doubled Hilbert space, okay? So this refers to the h left, h right here. Okay, then I've chosen as a convention of what to call the left copy, what to call the right copy. I've chosen that tau tells me it goes in the direction of left to right. Okay, this is just a convention of what to call left, what to call right. That means then that tau is going down in the left copy and going up in the right copy. So that the Hamiltonian for the new double theory, so the total Hamiltonian for the double theory is h right minus h left. Where this is the Hamiltonian of the thermal system that we started from. This is the Hilbert space of the system that we started from, but we've doubled the system to construct something which is called the thermal field double state. Okay, this is just a definition of what this thing is. And so the claim is that through this construction, you can describe thermal physics by means of a pure state. And so this is what we can show next. Okay, in 5 minutes, yes. So to understand why it does that, let's look at the density matrix. So here's psi. So the density matrix of this pure state is just pure density matrix. It's just this mirrored picture like this, okay? So with a left, right, left, right. And the reduced density matrix that you get from tracing out the left copy will be the cylinder with just one open slit left. Okay, because you've glued the left part here and here. So, and this we know is our thermal density matrix that we started from, okay? So, this is very familiar because we just applied this to the calculation of the entanglement entropy. But it's a general discussion that starting from a thermal density matrix, you can construct a state whose density matrix has this form and has therefore the properties that the norm of that thermal field double state is equal to the trace of the thermal density matrix. So in picture form, this is the following statement that the norm of psi is taking psi and then its bra image and gluing them together. Okay. So it's gluing this together, gluing this together. That's equal to taking the thermal density matrix and only gluing this together, because both of those gluings will result in the same cylinder, okay? So here on the right is just a pictorial notation of the norm of psi equaling the trace of the thermal density matrix. And if I now add an operator insertion somewhere in here, I've understood the following statement as well, is that the trace of O times the thermal density matrix is equal to the expectation value of O in the thermal field double state. So in these two statements, 1 and 2, are really the two statements of the thermal field double physics. And, well, I could have left this actually. So starting from the thermal system, I could have also just stated a question here at the start of this section. So I could have asked the following. Is there a state psi which is a vacuum state that knows about the temperature of the system somehow? Is there such a state for which the QFT vacuum expectation value reproduces the thermal average. Okay. Trace rho O thermal. Trace O rho thermal of an operator O. Okay. So I could have asked this question, and then you would have to come up with this construction where you cut the cylinder of your thermal density matrix in half, because you can play with these path integral pictures now, and then we define the thermal field double state the way we have. Okay, because it's so the thermal field double state is constructed to satisfy this question, and the procedure is then called purification of your thermal system. Okay, so let me add some few comments, and then we can have a break. So, yes, maybe we can leave that here. One is the von Neumann entropies. So let me just say it in words. The von Neumann entropy of the thermal field double state, it will be 0 because the thermal field double state per construction is pure. So the von Neumann entropy for the thermal field double state is 0. The von Neumann entropy for one of the copies, for example, for the right copy, will be equal by the construction again to the thermal entropy. And so this is exactly what we've exploited in our version of the calculation of the entanglement entropy just before. Okay, so the von Neumann entropy of one of the copies is equal to the thermal entropy, and it's equal to the entanglement entropy between two doubled copies of your system. Okay. Between the left and the right copy. So that's one comment. The other one is the mathematical construction, which is really just one line. But I prefer the pictures myself, but if you prefer the mathematical construction to remember, then it's this. So given the thermal system, so a thermal density matrix, which is a mixed density matrix of this form, which you can write explicitly like this in terms of the energy eigenstates of your Hamiltonian, which you called HR, okay, with probabilities Pn is e to the minus beta, the eigenvalues, energy eigenvalues. This is the system you've been given. So let's write our thermal field double state in terms of those ingredients. So then we write it just as sum of n Pn, a left copy and a right copy, like this. Okay, so what you see immediately from this is if you take the norm of this thermal field double, you will get the sum over the probabilities, which gives you the trace of the density matrix. So this is what you want. And so that's why there's a square root here. And pictorially, there's a square root here because you're preparing the state by path integration over half the cylinder. Okay. So this is a good time to take a break. And then questions first, or? Yeah?
Could you say once more why the time evolution is given by Hamiltonian?
Yeah, one up and one down. So because I've chosen the convention that my Euclidean time goes from the left copy to the right copy. So it's turning in this direction, meaning that here, where the left field configuration lives, my Euclidean time tau is going down. And here it's going up. And if I go to actual time, I will set tau equal to I t. There's a reason why I put an S here. It's just, I don't want to call it t, which is our Lorentzian time in figure A. But just another Lorentzian time. There's a plus or a minus here. This will inherit the directions of tau. So the corresponding Hamiltonian will be h right minus h left. Yeah. Okay, so we can take a break for 10 minutes. Yeah. Okay, so we can start again. Okay, so all we've left is the thermal field double state here. To remember that it's half a cylinder, okay? So we started from a given thermal system with some reduced density, thermal density matrix, which is just the cylinder with a gap. And our thermal field double state that we construct is constructed as half the cylinder. And so I'm emphasizing this again to sort of make the general point that in general you can do such a thermal field double construction if you have a manifold that can be divided into two disconnected pieces only by specifying two values of its coordinate, okay, of one of its periodic coordinates. So I'll write it down. So the TFD construction can be done in Euclidean manifolds that can be divided into two disconnected parts by specification of two values of, in our case, tau. Okay. But more generally, a periodic coordinate, tau. Okay, so these are the two values that I called tau 0 and tau 0 plus beta over 2. Okay. So the example that we had on the board was that of a cylinder. So this was for an uncompactified spatial direction xz. If your xz were compactified, we could remake all these pictures with tori instead of cylinders. And some more examples that I want to discuss now are the Euclidean disk and the cigar manifold. And both of these appear in the context of the Unruh or the Rindler effect. Okay. which is what I want to discuss next. Okay, so this is my next section on the Unruh effect. And the first example here is looking at a theory on the Minkowski plane. So let's start with just a simple planar geometry minus dt squared plus dx squared. I'm not going to add other dimensions, but of course you could if you wanted to. Okay, so, but we'll just work in 2 dimensions. And as I emphasized yesterday, if I give you metric or you give me metric, you need to also specify the ranges of the coordinates, okay, for me to know what it is that you're actually talking about. So this is the plane. Let me draw some pictures. This will not work for the recording. Okay, I'll do it anyway. So I'll draw some pictures here, but I'll change the board in a bit. So this is the Penrose diagram of this geometry. It's the large diamond. I've already divided it in smaller diamonds, which is of no concern at the moment, okay? So this would be my t direction and my x direction. What I mean by that really is that the constant t lines are these hyperbolic lines. These are constant t, and constant x lines are the dashed ones like this, okay? This is what I mean by writing the x direction to there and the t direction to there. But it just, if I'll have to add things to the middle of this figure, and therefore I don't want to crowd it, okay? This is just the Penrose diagram or conformal diagram for this geometry. Let's now consider a boosted observer, so boosted or accelerated observer. So with some proper acceleration a in the x direction. And such an observer only has access to a Rindler wedge. So I'll show that in the figure in a second. Let me first write the geometry of the Rindler wedge. So this one would be the big diamond. Okay. So it's a part of this geometry for this restriction of the coordinates. And so I can further rewrite that. Like so. So by doing the following coordinate transformation, Okay, and in the last step I did one more coordinate transformation where I write r as the exponent of some x. Okay, so these are some different ways in which you can write the Rindler geometry. Okay, the way to remember this coordinate transformation is that if we were in Euclidean signature, I would have sines and cosines here and just a disk geometry. I'm waiting for it to stop. Good. So the Rindler wedge in that picture is a small diamond. Okay. So the right Rindler wedge would be this, and the left Rindler wedge would be this one. So this would be the left one and the right one. Okay. So let me draw it separately. I have the Rindler wedge. The right one with now this time that I called TS. If that one runs over its full range, then it covers this only this small diamond. So these are again the constant timelines would be these. I said it wrong here, I think. These are the constant timelines, of course. These are the constant x line. And xz in this direction, okay? So in this other coordinate r is 0 would be here, r is infinity would be here. Okay. To talk about the thermofield double construction, I want to go to the Euclidean manifold. So let me do again a Wick rotation to Euclidean signature and write the Euclidean Rindler geometry as dr squared plus r squared d tau squared. Okay, now what are the ranges of those coordinates? I still have that r has to be positive. And this tau now has a periodic range from, let's say, 0 to 2 pi. So it's clear from seeing the metric, again, that tau has to have this range, has to be periodic with a periodicity 2 pi. In general, you would have to be careful and check what the right periodicity is for this manifold to still be smooth. We started from a smooth Lorentzian manifold, so which would be a solution of Einstein's equations with no weird source terms that could cause any conical singularities. So if you go to the Euclidean signature, still this should be a smooth manifold. And it only is if it has this particular periodicity 2 pi, because otherwise you have precisely this picture again that we had before, because this is precisely the disk in polar coordinates that if you would try to identify in the tau direction before you hit 2 pi would generate a conical singularity. Okay? So this is why this range is important. I've told you that we're looking at the region that an accelerated observer with acceleration A has access to, namely this Rindler wedge. But I've subsequently set A equal to 1. So I can bring it back in some places. So if you bring back A, then it's here, 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 and so here. So that in general you need the periodicity to be 2 pi over the acceleration of your observer. Okay. So the point as before, just to repeat it, is that this is a Euclidean disk. If we are careful about the correct periodicity, and since tau is periodic, there's some temperature in the game. Okay, as soon as you have a periodic Euclidean direction, there's some temperature. So there's some thermal interpretation of this, and that thermal interpretation is the associated temperature of the Rindler wedge. Okay. So let me draw. Okay. Let me draw the Euclidean geometry. So the Euclidean geometry is in R is 0 and goes around like this. Okay. So let me add the coordinates. So sorry that the second and the third picture are touching. They're not supposed to, of course. But okay, here we have Euclidean Rindler in the tau coordinate. I like to draw the tau coordinate always in the same color. So my tau goes like this. Just because it plays the role, it always plays the same role in these different sections that we're discussing, okay? So this is my tau direction. Then I have the Rindler wedge. So this is the conformal diagram or Penrose diagram for the Rindler wedge. And this is the conformal diagram for the flat space, the coordinates t and x. Okay. So from the thermal field double construction perspective, there's a thermality because we end up again with a Euclidean manifold that can only be cut into 2 disconnected pieces by specifying 2 values of a periodic coordinate tau. So here that would be tau is 0 and tau is pi, let's say. So let's do exactly that and cut our manifold to make a thermal field double description of this thermal system. So what we call the thermal field double state, so I could also call it this thermal field double state, is that manifold cut into 2 and path integrating over the lower half, okay? So that produces a state that lives on this open dashed line that can take on a field configuration boundary condition here on this region and another one on this region, which I can call phi left and phi right again, with tau going in the direction from left to right according to our conventions. Okay. So if you prefer the formula, we make this thermal field double state where there's a temperature in the game which is 2 pi over the acceleration of our observer. So our Rindler observer is an observer that only has access to this wedge in the middle picture of the plane, and there measures some temperature, which is the Rindler temperature. It's 2 pi over A, or A over 2 pi. And the energy levels are the energy levels of the Rindler Hamiltonian. So which I would call the Hamiltonian with respect to Lorentzian Rindler time, which we can call H right for the Rindler wedge, for example. Okay. For the right Rindler wedge, for example. And so then the Rindler or Unruh statement is the following. Is that the vacuum state in the Minkowski plane gives you a thermal state in the Rindler wedge. Okay. Okay, then now let me, questions. Then now let me just draw a picture of Euclidean plus Lorentzian evolution of a state. Which is basically superimposing some of these pictures, okay? So the statement is, I can prepare my vacuum thermal field double state as such. It is so that, okay, in thermal field double language again, this state is constructed so that if you trace out the left copy from the density matrix, that you get a thermal reduced density matrix as seen from the right copy. So this is the TFD version of the Rindler or Unruh statement, okay? So you get that this is equal now to, this picture, okay? So it's rho thermal with beta is 2 pi over A. Well, we can also do this maybe on the other board. Okay, so what you will typically see or do is combine the top and the, so on that picture, You take the large diamond, which is in Lorentzian signature. So the time is 0, t is 0, slice is here, okay? That one coincides with the tau is 0 and tau is pi slice here, okay? So in the Euclidean signature. So you will often superimpose this picture and this picture, which is what I'll do now, such that they meet exactly at those lines, at t is 0 and this line. Okay, so here is 1/2 of a disk that's coming out of the board and preparing the vacuum state on this dashed line in the middle at t is 0, okay? So my tau direction is in this plane like this, okay? Goes from there to there. So this would be psi at time 0, which I've prepared as a thermophile double state. Namely this, I'm just superimposing this picture on the first picture, okay? So this would be at Lorentzian time equals Euclidean time equals 0. And then I can further evolve this state to a later Lorentzian time. So if this was obtained by evolution in this direction, so if this is the TE direction, with TE equal to minus IT, okay? So also in the previous pictures, I wrote that one in blue for the evolution direction. So this is it's just the arrow pointing towards the dashed line, okay? That's the Euclidean time, which is Wick rotated to this Lorentzian time of the full diamond, okay? So this would be the state living at t is 0, and then after evolving for all this time in Euclidean time, when you hit this this location, you can start evolving upwards in Lorentzian time, and then at some later time, you would have a state living at this dashed line. At some later time, TA, okay? So let's say that this is T is TA. So that one you've then obtained by evolving first in Euclidean time, then going a bit further in Lorentzian time. So let me add that tau is minus I, well, this S actually stands for Schwarzschild, but we'll do that one next. So this is your Lorentzian Rindler time. It's the time of an observer that only has access to one of these wedges. Okay. So who measures a thermal system? Because its continuation is a periodic time. Right, so this is something that maybe I should have added to the previous picture with the two wedges. Well, I didn't add it because I only had one wedge drawn here, but in this picture, T goes up. Let me not use the tau color, but the time in this wedge goes up. And in the left wedge, the time goes down, okay? So this is precisely because your total Hamiltonian is h right minus h left. And so in this picture, it's because tau is moving backwards here, so its Lorentzian version is going upwards, and tau is coming out of the board here, so its Lorentzian version is going down here. Okay. So one other picture for this is that people often write this in one picture, so you would have some Euclidean evolution until here. And then if you want, you can keep evolving in Lorentzian time, okay? So this would be here a psi written as a combination of Euclidean and Lorentzian evolution.
So this is just using the lower half, right? There's no other difference?
The only difference is that I've indeed lost this lower half, and then I don't have to picture this coming out of the board, but I can yeah. So in this notation, this is the Euclidean solution, and this is the Lorentzian solution. And you just don't mind that there's a right angle between them. As in your picture, you don't. Okay. Okay, the second example is to look at QFT not on Minkowski space, but on a Schwarzschild black hole. Thank you. Okay, so this is the Schwarzschild black hole in Euclidean signature. We have some periodic time tau.
What is the variable you're using then? Is it the mass?
This is the horizon radius, so it's what you call 2m. But I write it as the r sub h. This is r sub h, yeah. So let me again draw a Lorentzian picture and a Euclidean picture. So okay, so this is the Penrose diagram of a Schwarzschild black hole. In the sense that this geometry is really like the Rindler-like coordinates that we had for the Minkowski space, and is only covering one wedge of a bigger space-time. That bigger space-time, so if I would have to give you some other coordinates which are called Kruskal coordinates to write the full extended diagram. So I would have to give you the equivalent of t and x in Minkowski space. But okay, I'm not doing that. I'm just giving you the Rinder-like coordinates, which are the Schwarzschild coordinates for an observer only having access to this outer horizon region. Okay. Let's look at the Euclidean signature Schwarzschild geometry, which is this one. At infinity, so taking R to infinity, we have a geometry details. So I don't care about these spherical directions, right? So they are there, but they are suppressed in all the pictures, so we don't care. Asymptotically, I have a d tau squared plus dr squared. Okay. So I have a cylinder in the tau and r direction. So if this is my tau direction and here's my r direction, asymptotically for large r, it looks like a cylinder. Okay. I'm trying to draw the tau r figure for the Euclidean Schwarzschild black hole. Okay, now if I lower r and I get close to the neighborhood of the horizon, this term will vanish. So asymptotically, I don't have this part, so I have a d tau squared, which is an uncontractable tau circle. It has a radius 1, so it's an uncontractable circle. But as I go deeper into the bulk, this is something that will vanish eventually. So as r reaches RH, this direction just pinches off, and my tau direction will cease to exist. So this whole thing will go to 0 at R to RH. Okay, so this means that you typically have what is called a cigar manifold, where here at this point, which is the radius, R is RH, your tau circle becomes contractible. So you had an uncontractable tau circle asymptotically, which becomes contractible at the horizon, really. Okay. And I've drawn this here as a smooth pinching off, but there's no cone. The reason why there's no cone is because I'm going to choose the periodicity of my tau direction such that there is no cone. So this is something that we can do in the exercises more explicitly. But really, by doing some coordinate transformations close to the horizon, you will see that this tau r geometry takes the form again of a Euclidean disk, which for the right periodic identification of tau is smooth. So just again, the exact same picture. For the right periodic identification of tau, it's smooth. Otherwise, you would make a conical singularity. That is not allowed to be here because we're talking about a smooth solution of the vacuum Einstein equations. Okay. So the coordinate ranges, which I haven't given you yet, are r bigger than RH, and tau has to go from 0 to beta, where beta is some particular number in terms of the given parameter RH, namely 8 pi gn. Okay, so this is exactly the only periodicity that is allowed to avoid a conical singularity. Okay. at the tip of the cigar. Okay, so I will make it like this, so it's clear that this is the Euclidean version of this wedge. Okay, so this is the version, the Schwarzschild version of the Rindler wedge. Okay, so this cigar-shaped manifold is what you typically find in Euclidean black holes, because you typically have a factor like that. That behaves like that asymptotically it gives you an uncontractable circle, and near the horizon it pinches off like so, okay? So the cigar is asymptotically, for R to infinity, a cylinder, and near the horizon it is flat. Okay. Okay, so this cigar manifold is again a Euclidean manifold that you can divide into two disconnected pieces by specifying two values of this periodic coordinate tau. And if you do that, you can write down a thermophile double state. So let me try to draw this. No. Okay. So I should stop about now, probably. Or so I'll try. Okay, so this is supposed to be half of the cigar. Here's where the horizon radius is. Okay. So the right part would be a part that I draw in red, where a right field configuration can live, and here where a left field configuration can live, okay? So this up to normalization, which I'll add now, is the Harder-Hawking state. So the normalization is not in the picture, but I'm adding it in the formula. So this is the Harder-Hawking state of quantum fields on a black hole background. Where, okay, z of beta is your partition function, so it's a trace of e to the minus beta h tau, and these energy eigenstates are the ones of your Schwarzschild Hamiltonian. HTS, okay. So I'm reusing the same notation for different things because the same, they play the same role every time, okay. So 2 minutes. So again, you can write Euclidean and Lorentzian evolution. Where's my Lorentzian picture? It's already gone. So I can do Euclidean plus Lorentzian evolution superimposed, or I can get rid of the lower half of the Lorentzian picture and write this as this. Oy. This. Okay. So we're here. This point is my horizon. I'm doing Euclidean evolution over half a cigar. So to make these pictures, I'm looking at the cigar from this point of view, okay? So if I look at it from that point of view, it looks like a disc, half a disc with the right configuration on the right and the left configuration on the left, okay? So if I add the pictures, this will be maximally clear, okay? The colors, okay. So this is your Hartle-Hawking state in a picture. And next would be to apply this to an ADS Schwarzschild black hole, in particular in 3 dimensions. It's called a BTZ black hole. And this will be moving us to holography, which is where we're going next. But that's for next time.